we're going to get going on some material which will be handy for the first assignment as well as for the next take-home exercise, which will be on Tuesday. Okay. Folks will remember, I hope, from the last lecture that we had finished our lecture with a look at certain canonical, very important, very widespread, and very powerful higher order functions. What were those three higher order functions we examined within the Scala context? Map, reduce, and filter. And these are functions which you will find appearing not just in Scala, but in a wide variety of programming languages. And indeed, variants of them form the basis for a lot of today's high performance computing infrastructure and software. So when you think about MapReduce algorithms and this, and we'll talk a little bit about why this is in the course of the lecture. But I first wanted to try to help us recall a few basic elements of these and try to recall how we can use them, combine them in a way that that yields something where the whole is greater than the sum of the parts. So we're going to be operating here within the Scala context, as we are for much of the semester. And within Scala, we have a set of collections, or indeed, more broadly, a set of containers, which contain elements of particular sorts. And broadly, there's two big sets that you could characterize. One is an immutable set of collections or containers. These are things that contain items, and the items that are in there cannot be updated. They're immutable. We'll come back and talk about why that's so important later in the class, why that really helps effective software engineering. But Scala also, being a multi-paradigm language, provides a mutable collection hierarchy. Okay, and we're having a bit of clipping issue over here on the left that I think we'll have to bear with. So we have some collections as well, which have analogs in both, so immutable, mutable, and we have some that appear in only one. An example would be array sequence. Array is a little bit on the borderline in the sense that its size is something that's fixed, but the elements within it are changeable. We have array sequences, stacks, etc. So we're going to have both those hierarchies, and it turns out that map, reduce, filter will be able to apply pretty much across these hierarchies, as well as across several other types of containers in Scala that we'll be talking about in a big way when it comes to error handling and when it comes to encoding exceptional values, etc. Now, we've been relying for much of our work on arrays just kind of by force of habit. But you should realize that Scala's hierarchy of collections does not privilege in any way arrays. So these are kind of the recommended standard collections for certain needs. So if we want something that's immutable and we want to be able to look inside of it at an arbitrary position really quickly, we're not going to always just access it sequentially. But we want to be able to kind of go in and grab something from chosen elements within there. A vector is, in fact, more recommended than array. It has much more favorable performance under certain circumstances, and it has some additional sort of complexity associated with it to help it help it scale or help it operate under a variety of different needs. Sequential access, meanwhile, you would use a list. That turns out it's an immutable data structure. So if you want to add something to the list, at the end of the list, what do you get back? A new list. You append it, and that's a new list. Mutable data structures, we have array buffers for random indexing, and we have list buffers for sequential access. We'll come back and see some of these later. And as we'll see, we'll have a variety of different types of collections here, which are very powerful collectively, and we'll actually use a number of them without really talking about it. So we've already used arrays quite a bit. We use vectors a little bit. We might be seeing maps today. Maps are things that, like a dictionary, you have a key and a value, and maybe it's names and the person's age. And you can look up the name and find the age. Or maybe it's indications of the make of a car and the year it was released or what have you, right? So this is a map from a key to a value. And we have a very nice way of writing those in Scala, as we'll see, where you use this kind of arrow notation. So square is associated with this function. Cube is associated with that function. This is a dictionary that maps strings associated with the name to the function or closure that implements them. We also have vectors, I've mentioned that, and streams as well. We're going to be spending quite a bit of time on streams. And we might even see something on them today. But the key hallmark of them in the context of collections are going to be, they're the foremost example of a lazy data structure. And Scala supports laziness. Supports, more technically, non-strictness. Meaning that we can specify computations that are potentially infinite and evaluate them only incrementally as we need them on an as-needed basis. I think some of you will have seen laziness in 340.
Yeah,
right?
Haskell.
Yeah, in Haskell. And Scala supports that in a fulsome and quite beautiful way. And we'll be spending quite a bit of time with streams. They separate out, on the one hand, the ability to specify an infinite computation from when that computation is evaluated. And on an as-needed basis, you can do as much or as little work as you want, while still having clarity about, about the whole computation. We're also going to have these ranges, integer ranges and numeric ranges, which are going to be very handy for creating sequences. Yeah, like we'll be using this one today, 0 to 1, with a step size of 0.1. Okay, we're going to come back to these, but I'd like to return to these key operators, and we're going to go through several additional of them today. And there's one of them, flat map, that has a especially powerful purpose associated with it that we'll come back to in a few more lectures, associated with something called monads, okay? Which are an extraordinarily powerful mechanism that allows us to build extensible software that's very, very clean as well. But the main ones I wanted to introduce last time, and that we're going to follow through most of today, are map, reduce, and filter. So broadly speaking, what does map do? So if I give you a collection, or indeed more broadly a container, what does it take and what does it return? What does it need to do its job?
It gives a container, applies a function on each element of that container, and returns that function.
Okay, good. So we might start with a vector of, okay, let's do it, right? Let's do it. Let's just remind yourselves. Okay, go to the Scala console here, right? And let's create a vector of numbers. Now, we've been doing it by hand, right? We could do vector of 1.0, 1.0, 3.14, 159, and 2.71, right? And we could get back a vector here. And that would be fine. Let's do map of, how would I do map of, to square all those numbers? Take this, how about the square root? How would I do that?
Underline, multiply, underline.
Okay, how about, well, okay, say square, that's fine. No, we can't do this. What's the meaning of that? Why will it be an unhappy camper if we do this? It's tempting to think we can, to square them. Yeah, it's taking two arguments here. Each of these is a separate one. It's looking for two. So what do we have to do instead if we want to square it?
Use a named variable.
Yeah, named variable. And this named variable is the start of a definition of a what? Anonymous function. How do I write that? Okay, d times d. Okay, great. There we go. All right. Okay. Great. So we could do that. Alternatively, we could try to perform a square root here. Now, this is actually going to cause problems because it's, I don't know where a square root is. So we'll do Scala dot, I think it's dot util dot math. Or is it Scala dot math? Scala dot math. Yeah, thanks. Hey, and lowercase. Thank you. Okay, there we go. It's not a member of double. Okay, so mumble. Square root.
Square root takes the value itself.
Sorry? Oh, yes, of course. You can't apply it. You have to. Thank you. What we could do is do instead what? This. There we go. There we go. Happy. Okay, great. So this is a shorthand way of basically saying take an argument, which I'm not going to name for convenience, and whatever it is, take the square root. Okay? Great. So there we are. We have a little thing, but we could do this in another way. We could, for example, do, and I'm going to parenthesize this just so it's clear, 0 to 1.0 by 0.01, and we could take the square root of each of those, right? There we go. So this is creating a collection of those going from 0 to 1 with an increment of 0.01, and we're mapping it. And when you're trying to understand these things, it's often convenient to kind of, if you're having trouble understand them, just if you have a whole sequence, strung together, cut it down so you only see the first couple or just the first, and so you can follow the logic here. So it starts with this, and then it applies a square root operator to it, right? Conceptually straightforward. So that's map. Okay, how about reduce? So how are we gonna? Suppose we wanted. What would we use reduce? What does reduce need? What does it take to do its job?
It's a reducing function.
Reducing function.
Collection and usually the default element or a starting element.
Okay, yep, you can certainly do that, and there are a bunch of varieties of that. The reducing function is different, I would argue, than the function I gave map. Why is it different?
Does it return the single value?
Sorry?
Return the single value.
Okay, returns a single value, but square root of a number is a single value, so you're getting close, but what's the difference? The reducing function takes two arguments. It takes two arguments rather than one. This guy takes one, but we want something that takes two and turns them into one. So you got the basic idea of it there, but the difference is that it takes two and turns them into one. And by so doing, it's kind of summarizing those two with just one value, right? So we might use it, for example, to add up these numbers. So how would I do that?
Underscore plus underscore.
Yeah, exactly. Good, good. I could just add them up like this. There we go. Ghost would have seen it first. But ladies and gentlemen, we've just summarized these numbers, these many numbers, with one value, and that value was given by successively applying this operator. Right? Comfortable? Okay. So that's reduced, and there's many varieties of this, right? Many varieties. We could, for example, use this to concatenate a bunch of strings, right? Let's do a vector of strings, right? Foo. What's next? Bar. Okay, how about the third? Baz. And the fourth? Yeah, you can't miss that. Okay, so let's reduce. And how are we going to do this?
Probably do it the same way, assuming concatenate is a plus sign.
Okay, yeah. So it actually turns out we could in fact do this thing to append them, but we in fact can use it like this. So there we go. Okay. Okay, so here we're concatenating them all. The plus here is being used to mean concatenate. And it's not that it's loosey-goosey about it, it's just that for strings, plus is defined to concatenate. It's got a different meaning in that context. Okay, so this is good. Reduction can be used for many summarization operators, many things that take in many and return one, right? Good. A final one is filter. How are we going to apply filter? So let's suppose that what does filter need to do its job?
It's a function for checking true or false.
Yeah, so it is a predicate. It's something which determines for each value, is it qualified to be included? Does it pass the test? And if it passes the test, then how does that differ if it doesn't pass the test? The ones that pass the test are what? Included in the result. So it's mapping, in contrast to reduce, which maps a collection to a single value of the type of the appropriate type. It's not a collection. Filter takes this binary, the Boolean returning function, and it returns back a collection, right? Okay, so let's filter the set of these ones here whose square root is greater than 0.75. How do we do that? Well, okay, let's start. Let's filter it to take the set to only get those whose value is above 0.75. How do we do that? Let's do that first.
Underscore greater than.
Okay, good. Okay, excellent. Good. There we go. Boom. Okay. How if we want to have those whose square root is greater than 0.75? Give me two different ways to do that.
Nest a map into a reduce.
Okay. Okay. So I like that idea. But would we? Well, okay. So I like the idea of combining the two because there's a map there. What's the map for?
Square root.
Square root. But would we put it inside of the filter?
Before the filter.
Before the filter. Ladies and gentlemen, there's going to be a pattern here emerging again and again. So we're going to take the square root. Oops, sorry. Man, word only so. Okay. And then we could filter those. Okay, that's actually not going to though give us all of those whose square root is greater than 0.75. It's going to give us the square root of all of those, right? So if we want to get them back, we would have to square them again, which is not so elegant, but it's going to show a pipeline style that we're going to come back to many times. How would I get those whose square root is greater than 0.75?
Square root of the interval.
Yeah, so we could do square root of this, right? And now we're getting the elements whose square root is greater than 0.75. Huh? Okay. But that idea of putting them in succession, of having this kind of pipeline where one thing does it first, then the next, and then the next, is going to be extremely common. So I'll give you a little challenge here. How would you take this and do a sum of squares of the elements here? I want to have a sum of the squares of all the numbers here.
So you get the map sum of square.
Okay, so do a map, and what is the map going to do? Okay, so we'll do something like this, and then reduce to do what? Good. To sum them out. Okay. Pipeline. Yeah.
This is probably a little bit past what you're going to be talking about, but will the Scala compiler find cases like this and do fusion on them? You aware of that?
We're going to be handling that in a very fulsome way in a few lectures.
Okay.
Okay. And the answer is that it can do that under certain circumstances where the incremental computation is allowed and explicit. But this is one of the big benefits, performance-wise, of using streams, because it's on demand. It allows each element, rather than having this collection. So let's sort of illustrate this here. Rather than starting with that collection here, boom, and then going to this collection, boom, and then applying the final operator to get the result. What you're going to be able to do with streams is, in fact, handle, because it's on an as-needed basis, handle going through the entire pipeline with each element at a time, okay? That doesn't mean it can't be done in parallel, it can, but successively going through, it can be handling multiple elements at the same time, just in a pipeline fashion. But instead of creating whole collections one at a time, you're going to take each element, successively map it, reduce it as far as it will go. And what that allows is sort of the incremental computation of this, where you don't have to compute the full, successive collections. You can essentially just map the individual elements successively with operations along the way. And that means you don't have to keep giant data structures in memory successively.
Do you run into semantics problems when you do that? Because functions in Scala can have side effects, is that correct?
This is correct, and you need to be cautious about the side effects. But no, I mean, it can't be used willy-nilly with things with side effects. And there is a well-defined semantics of it, but when you're dealing with parallelism and you're dealing with laziness, there's extra levels of complexity there. And generally, you want to be doing these with pure functions, with things that don't cause side effects and change their behavior successively. We will see how we can combine them with things that have side effects shortly. Okay, what's that?
Is traverse a function?
So traverse, there's something similar to traverse that we'll be talking about, okay? And we'll see how that can be applied actually in the context of laziness and side affecting operations in a fruitful way. Okay? Yes, question?
In Scala, by default, is map a parallel function, or does it do sequentially?
Great question. So it can be applied in parallel. It depends on whether it in fact is applied, depends on the type of collection that it's applied to. And one of the things you'll see is that Scala directly supports parallel collections with a minimum of fuss. So this right now is not being evaluated in a parallel way. This is being applied in a parallel way. So all I'm saying is, so let me distinguish those. I put in that par here. Here we go. Notice this is a numeric range here, right? If I put this in dot par, now I'm getting a parallel sequence. And what that means is that this sequence can be applied in parallel. Okay? And we'll come back and talk about that. Maybe I'll talk about that a little bit right now. So it's a very prescient question in today's world. And indeed, much of the motivation for use of Scala and for use of functional programming is effective, scalable computation, scalable in terms of the number of data items. And ladies and gentlemen, you are entering into a world professionally after you leave here where it's very routine to manipulate millions and millions of data items in parallel, or millions and millions of data items at a time. And one of the best ways to do that is, if you can do so, is to do it in parallel. But it also brings up some very important needs for doing it in a memory-constrained way. Because with millions of items being manipulated, it's very easy to max out the memory associated with a computer. And it turns out that parallel structures, such as this, are one step forward, and laziness is another, for the reasons that Chris was asking about earlier. It allows us to do work in an incremental way rather than creating whole collections. So if we have a collection here, and without privileging it, I'll draw it as kind of a vector. And we have these individual items in here, and we do a map. We are taking each of those items and bringing it into a corresponding item here. And this is what we call an example of an embarrassingly parallel circumstance, right? Each of these maps, one item to the corresponding item in the output, each of those can occur in parallel. They don't depend on each other. They should, if well defined. And as a result, they can be parallelized. If we had at our disposal different computing units that can handle these in parallel, we could apply them to different chunks of the array. It's not necessarily each one, but we might associate the first 500,000 with core 1 of your machine, right? The second 100,000 with core, or second 500,000 with core 2 of your machine. So you can have multiple cores operating to map different chunks of this original container at a time. Or maybe this mapping is a very big one. Maybe it's one that's that involves a lot of operations itself. Maybe that function is quite involved, in which case you might even want to have a processor handle each of these different processor assignments. And Scala is one of the best languages for undertaking things like that, and it hence the name. Scala is a portmanteau of scalable language. Okay? It's scalable. And it's one of the reasons it lies at the heart of the Spark system for very large scale computation, which is the focus of another course of mine, but we'll probably refer to here and there. So here we're performing this mapping. How about filter? Is there an opportunity for parallelism in filter?
Yeah.
You bet there is. We can evaluate whether each of these elements in turn passes this predicate in parallel, right? Each of them, whether it passes or not, doesn't depend on a need to process the earlier elements. We could divide up different sections of it to be evaluated at once. How about reduce?
It cannot be parallelized to this degree.
Cannot be parallelized to that degree, but what could happen with reduce? let's suppose we were adding up the elements of this array. How can we at least extract some parallelism to it? After all, why isn't it totally parallel? Reduce.
Because it's depending on the previous value.
Yeah, the value we get back almost by its very definition is the summary of all the elements, not just one at a time. It's the summary of all of them. And it needs information at some level about all of them, right? That value you get back, the sum of the numbers in the vector or what have you, it depends on all of them. So what can we do to elicit at least some opportunities for parallelism here?
Well, if you assume associativity of your operator,
Ah, yes, exactly. So if we assume associativity of the operator, what can we do?
then you can do a reduce on each chunk individually. You can chunk it up.
That's right. So when we talk about associativity, ladies and gentlemen, if we consider, and if we consider these elements, added from index 0, 1, 2, 3, etc. So this large sum of the a sub i's, where I goes from 0 to the count. So I'll write n minus 1 here. We have this. The question is, are they associative in the sense that, and I'll just for simplicity of writing it, I'll consider the first three. Is this the same as this? And in fact, Scala, the way these things are defined in Scala with the well-defined semantics, does assume associativity. Okay. And so, if you're using reduce, you could use reduce left or reduce right if you want to be more specific about it. And there's a fold left and fold right, which are related to that. But the point is, if you can assume associativity, what can you do here? Well, let's imagine at the smallest level, we could add these two together in parallel with adding these two, in parallel with adding these two, in parallel with those two. And the next level up, we could be adding these two together in parallel with these two. And by successive pairs, we can go down and reduce the whole thing down to, at the end, some final end, right? What's the depth of this tree? Yeah, it's proportional to the log of the number of here, log base 2 of the number. And indeed, proportionality is proportional to log base n, where n is any number greater than 1, right? So it's proportional to the log here. It's O of log n in terms of depth here, okay? The depth of this, which means in that many steps, we could reduce it with this parallelism. We can't do it. It's not embarrassingly parallel in the sense we could do all at the same time, but with successive ones, we could certainly eke out a lot of parallelism. Right? That makes sense? So in Scala, we have this ability to say, hey, make use of a parallel implementation, which allows this to run this on multiple cores. And yeah.
Is that for the mapping or?
No. That par is, it's a great question. Is this par for the mapping? No. This par is saying render the collection at this point as a parallel data structure. And the fact that it's a parallel data structure means that when we apply successive operations on it, they can be done in parallel safely. We wish to exploit parallelism.
Is there a way you could do selected functions in parallel and not? So if you want to get the map done not in parallel and the filter done in parallel and those kind of things?
Well, once you are in a parallel context, you could ask it, you could do a successive series of operations in parallel, and then you could ask it to create a non-parallel version of those and apply other operations. So you could go back and forth between parallel implementations and not. It would be a little bit cumbersome, but generally you are operating with a set of data that you either wish to allow for parallel operations on it or not for a sequence. So it wouldn't be, horrendous. Once it's a parallel side, the operations you perform successfully until you unparallelize the data structure will be done in parallel. So you can switch back and forth if you wanted. Okay, that'd be the way that comes to mind. Now there's lots of other mechanisms we'll be seeing, in fact, in Scala, which will be also used for parallelism. So we'll be seeing, for example, futures and the use of futures, which provide a way of capturing more coarse-grained parallelism. So, for example, maybe you have your code and it's reading in parallel from 10 different web pages. It's grabbing the contents of those web pages and performing some computations on them. And because the grab of a web page, sucking it down into memory, it takes a certain amount of time. Maybe we want those operations to go on in parallel. And there we might make use of a future, which is kind of a promise that when you need it, I'll have the data for you. But in the meantime, let me just operate on it behind the scenes in the background until you actually need it. And so that's a way of getting asynchronous computation. Asynchronous in the sense that it's only guaranteed to be there when you need it. In the meantime, it can be operating on its own. Okay, so we'll see a bunch of ways to capture parallelism in different contexts, and I'll talk about parallelism in the context of laziness as well. Okay, ladies and gentlemen, so they'll be pipelined. So here we go. Okay, how about another example? Suppose I wanted to take that last thing that I did, the sum of the squares. Here we go, sum of squares, and you could do it in parallel or not. And suppose I want to take the square root of the sum of the squares. Give me two ways I could do that. So I want to take the norm, the square root. It's like, square root, if I do it for x, y, and z, square root of x squared plus y squared plus z squared. So this is what we call the ultimate norm associated with that. And suppose I wanted to do that. So right now we have the sum of squares. How would I take the norm of it? How would I take the square root of this? Give me two ways.
Just wrap the whole thing in a
Just
square root.
wrap the whole thing in a square root. Could do this. And we're in good shape. What's another way I could do it besides wrapping it up? What's a more pipelined way I could do it? Well, among other things, I could do what?
Can you map over a single element?
Yeah, unfortunately, it's a nice idea.
Is there an apply?
And there is, in fact, yeah. There's something like apply. Suppose I were to do this. What's the problem? Oops, square root of this guy. What's the problem there?
No container.
There's no container, ladies and gentlemen. Yeah. We'd like to be able to do that, but it says, hey, I can't do a map on a double, right? Because it's not a container here. So we would like a way to compose two operators, okay? We'd like a way to combine them. And I'm not going to cover it here, but in the context of I think it's the next one that I'm going to be rolling out, the next take-home exercise, you're going to see a way to do a composition of two functions. So that will allow us to compose these things. Rather than wrapping it, we'll be able to have the compose of two operators so we can make them appear in a nice pipeline fashion. Okay, so those are some basic reminders of this. Let's see if I want to. Well, yeah, let's do one with filter. We haven't really tapped filter here. So suppose in a multi context. Suppose I wanted to take the. So import java.util.rand. Oops. Oh man. Gosh, what is it again? For rand, it's Scala util random. That's what it is. Scala util random. Scala util random. Oops. Okay, let's try this. Sorry? Is it, there we are, yeah, good. Okay, and here we can import everything in there using the underbar, okay? Everything within that. Now this allows us to do next double, for example, and this will generate doubles, okay? We could generate successive doubles. So suppose I wanted to, I'm going to do a vector, fill 100 elements. Now this one's going to be a little bit confusing to you, and it's going to be our first hint of laziness in one of its many forms in Scala. So here I'm saying fill a vector of 100 elements with double values that are randomly drawn between 0 and 1. Now what's a bit odd about this? If this sticks in your craw, it's for a good reason.
How is it randomized? There's no functions called.
Yeah. Wait, so
Figure
Laura?
out if it's lazy, then would you have to redetermine the value?
Yeah, so something seems a bit odd. I mean, if I said next double here, I get a particular value, and so you would think that this. Well, I mean, let's just try it, right? Okay, so I have 0.6. You would think that this might be something like doing something like this, but you know, that's definitely not what we're getting. It's actually taking this as what's called a by name parameter, and what that means is it's actually taking in not a number here, it's taking in a recipe for creating a number.
So it's like a stored seed, basically? That's
It's actually like a stored, it's like a closure to, that when you evaluate it will give you a number.
So if you just type a number, the closure is the number.
Yes, correct. Correct. This is actually taking in a, you could think of it as taking in a computation that when you need it will be run. Yes.
yeah, so like the question is like if you fill that to some ridiculously long number that can't possibly ever store memory. Let's say like 3 trillion, and you want the 1.5 trillion item.
Yeah.
Will it automatically remember how to get that because it's a random number, right?
No, it won't, but we'll see how with streams you can get something kind of like that.
Yeah.
Okay.
But it's random anyway, so you don't really care what it was.
Yeah,
It's close
yeah.
to-
I mean, in this case, I understand Warren's question though. That you know, does it need to actually evaluate the whole thing, for example, to get an element
Let's say
of
you
it?
need a lot of random numbers for one thing, but you want to re-replicate the same thing with the same random.
Same particular value. Yeah. Okay. So let's take this collection. So given that we can do this, and we'll come back to how we do this in a bit. It's very easy in Scala to create a by name parameter. We're going to go and we're going to take this, and I would like to take the. I would like to take the sum of all numbers whose square is greater than 0.75 here. How would I do that? Okay. Okay, what did I need to do first? I want to take the sum of the square of all numbers whose value is greater than 0.7. Excuse me. I want to take the sum of all numbers whose square is greater than 0.75.
You got to filter them out first before you.
Okay, we need to filter them. We need to filter them, but yes, okay. So
Filter based on the square.
based on the square, okay. So how would we do that?
Underscore, star underscore.
Square root.
If we did this, what would it be expecting? Something that takes 2 arguments. So we need to take in a double and then do what with it?
Square it and then compare it to points.
Square it, okay, d times d, and compare it to 0.75. Okay, good. And then, oops, then what?
And then reduce it.
Reduce it by adding them up. Okay, good. Oop, come on. There we are. Okay. Okay, suppose we wanted to.
If you run this again, you'll get a random number.
What do you think?
I'm assuming so.
Do you feel lucky?
Yeah.
Yeah.
So you're basically going to get any random number because they could all be above that, and then you get a giant number.
Well, this won't be any old random number. This will be drawn from a certain distribution. And certainly, if we said, okay, let's name this collection val, my rands or something like that, and then we were to do my rands here, every time that's going to be deterministic, right? My rands. That's going to be deterministic. But to be clear here, what I did was this. But each time, yes, it's recomputing it right now as it was given. Okay, so suppose I wanted to take the. Suppose I wanted to square all the numbers greater than or less than 0.5. How would I do that? We could do my rands here, and I want to have a collection that consists of the square of all numbers less than 0.5.
So filter for less than 0.5 and then map.
Okay, good. Filter for less than 0.5, and then map them to what?
Square.
Yeah. So they're squares, right? Or I could have, yeah. Okay. Good. Successively applied operators within a pipeline. If I wanted to go and multiply those out, I could reduce, right? Reduce by something like this. This is going to be very small. Good. Good. Ladies and gentlemen. Okay, so we've used those basic ones. I want to talk about a few more here. Okay. One I want to talk about is groupBy here. Now, groupBy is a little bit different from what we've been dealing with in a couple of different ways. One of the ways is that while it does produce a container of sorts out, something that contains values, it's a very special type of container. It's a map. It's a dictionary. Okay? And what we're passing in here is something that maps elements of the collection, the original container, to which we're applying groupBy, to keys. And the map that we get out is going to have, for each key that was produced by this function, the process of mapping, it's going to have a key, and that key will itself be associated with a container. And that container contains all the elements that map to that key. Okay, let's get a little bit of practice with Scala Maps right now. Okay, so val my map. Okay, here I actually have a slide on this back here. Scala Maps. So this is how you can, some ways you can manipulate maps, right? So here we're gonna create a map, for example, that will map from strings to numbers here, right? My map equals, and we'll create a map here, and it will go from A to to 1, and we'll go from B to 2. Okay, there we go. So this is a map, and having created that map, we can use it in a variety of ways. Among other things, we could do my map of A, and we'll get back 1. Why 1? That's the value associated with it. And we could, if we try to look up something not associated with it, it'll say it'll be unhappy. Okay. In general, there'll be a variety of other operations we can do here, and by doing an autocomplete, you can get a sense of those, right? So we could ask, for example, does this exist in there? And so it's okay. So it actually requires a collection. A pair there. Okay. So ladies and gentlemen, this is my map. This is a mapping from a string to an int. Okay. And we can, in fact, loop over the elements of it in a syntax like this, where we successively extract the pairs. We can also, for immutable versions of maps, place additional items in there, or for immutable versions, we can add new keys by sort of appending these and get back a new map. So if we have this and we want to add a new key, we could do so with something like this. Boom. Plus, and we could then map a new key to a value. Okay. C to B3 or something like that. All right. And this will be a map that comes out that has all 3 of those. Now, don't be fooled into thinking that this must be horrendously expensive. In fact, when you're dealing with immutable data structures, one of the things we'll be talking about down the road is they can actually be often implemented much more efficiently than mutable ones, because you don't have to worry about mutation. You can share a lot of resources. Just because these return different values doesn't mean they can't share things behind the scenes. And in fact, sharing is one of the things enabled by immutable structures. So it doesn't mean it's very wasteful in terms of space. It just means that you can't have observable modifications on it. Behind the scenes, there's often a lot of sharing that goes on. So here are maps. Okay, great. So having had that experience with maps, now let's see if we could use this information. So I'm going to go and we are going to create here so this will be some nums. Okay, we're gonna create some nums, and we'll go from 0.0 to 1.0 by 0.01. We had this before, and here we are. Here are my numbers. Okay, great. That's a collection. Now, I want to see, okay, what's the sign of each of these numbers? How would I do that? What would I do to get the signs of these numbers?
Filter.
Sorry?
Filter.
Okay. Okay. Sorry. When I say sign, I should spell it out. S-I-N.
Oh.
Okay. So how would I get the signs of these? Good. Sign of what? Yeah, I might as well just do underscore.
Do you need the underscore? Or is that implicit?
So if you did this, if sign is defined with a def, it's going to be an unhappy camper. If it's defined as a function, it's going to be fine. So in this case, it will be in fact. Okay.
What's the difference between a def and a function?
A def is not a function. Defs can be rendered into functions by partially applying them. You put an underbar after them, they can be rendered into a function. A def is a construct that occurs in the context of defining a procedure you could think of it as. And it supports a lot of things in how it's defined that you don't support in functions. An example would be multiple sets of parameters. Another thing would be you define and associate with type parameterization. Defs have a generality to them which can allow them to handle a variety of additional needs, but then they can be rendered into functions when needed with an underbar operator after it. And that basically is a partially applied function. And then you could treat them as functions. But they're actually separate sorts of things. And so if we did, like, watch this, def my sign, this takes in a sign, a double precision value, and it's equal to sign of D, right? See that? That's a def, and I could say my sign of 3.14159, and we'll get something very close to 0. Now, if I then try to apply that here, and I say my sign, it's going to not be, oh my gosh. Well, I'll be. Okay, normally in order to render, okay, I'll illustrate it another way. That's very interesting. I guess it does an implicit conversion there. Because normally if I say val, a function equals my sign here, it's going to say, can't do. Here, okay, here it'll actually treat it as a function.
Does that implicitly catch to a function of a single argument, or is it?
Sorry, yeah, it's a function of a single taking in a value, returning a value. Yeah. So by itself, this isn't a function. I can't use it like this because it will say, well, where's the argument and so on. In order to let it be treated as a value, I can say it's a partially applied value, and then it's a function. Then it can be treated and passed around as a function. Why it did here, well, you learn things every day. Well, I'll be. Because there are other cases where you need the underbar after it. So, beats me. Sometimes things work. Okay, so, ladies and gentlemen, so I would like here to, since these are the signs, we could do it with sign here. Here we go. I would like to now consider only those values whose sign is greater than 0.5. Or let's say 0.75, just to have a sparser array. So how would I filter these to be greater than 0.75? Well, 0.75, right? Great. Now suppose I wanted to take those and I want to turn them into right. Okay, I'm trying to think of a nice little example here. These are double precision values. We could quantize those into bins by basically converting them to a rounded version. But in the interest of time, I think I'm going to do this on a simpler example. What we're going to do is we're going to create a vector of, a foo of things of different size here. This will be a nicer example of it. Longer and long. Okay. There we go. And we are going to now do a reduce by, where we are going to reduce these. Maybe I'll put in another thing of size 3, just so you could see this bar. Okay, and I'll put in baz too. Here we go. So we have a set of operators here, and I'm going to not do a reduce. I'm going to do group by, and I want to group them by their size. Okay, so here I'm going to do this dot length, and what will come out of this? by my description previously, what will come out of groupBy? What's going to come out? A
A map with the length as the key.
okay. The length is the key, and what are going to be the values for a given key? The values are the
Collection of words that match that length.
yeah that have that length, right? So here, long has a length of 4. Foobar and Baz are all distinguished, not only in terms of their antiquity and trade significance, but their length. Okay, and here we have longer by itself. So here we have a map that basically groups. Just a second. They group together the items that have the same value for this function as specified by groupBy, right? Unfortunately, it's truncated there on the left-hand side. Let me just drag that over so you can see it. I had a underbar length here. So to be clear, for those not sure about underbars, what's going on is we're having, if you want to write it out more clearly, this would be we're taking in a string. After all, each of these is a string, and we're grouping them into bins according to the length of that string, right? And that allows us to get out this mapping from the length to the items that match those, right? Yes, so Chris.
I'm up there.
Okay, so let's try this now. Suppose I wanted to count the number that matched each length. So now I want to have, so right now I have a map from the length to the words that share that length, right? Suppose now I want to have a map instead from the length to the count of words that map that length, that share that length. How would I do that? What does it smell like? A map. And in fact, I could do it with map. Okay, now you might think we could do it with something like this. Map, and I want it to take this dot size or something. But what's going to happen if we do that? It's going to say, wait a minute, I can't do that because you've given me a function here that doesn't operate on values that are ints and vectors. Where does this int and vector, where did those come from?
The length of the word.
Yeah, this is it's treating the map as a collection, namely a collection of pairs of ints and vectors. 4 and this vector, 1 and this vector. Those are pairs, and those are the elements of the map when it comes to the map with a capital M, as we're applying map with the lower m to it. And so it's saying, I don't know how to apply a size to this. So that isn't quite what we want. What we want instead is map values. We're mapping the value side of it. You could also do map keys if we wanted to. You could filter it out by those that are less than, that are no more than 1. So here we're map the values. What does this 3 to 3 mean?
There are 3
There are 3
words.
words of length 3. There is 1 word of length 6. There is 1 word of length 4. Okay, so map values applies it to those individual kind of partitions there, which is nifty. And this is a trivial example, but it's an example that could be applied to millions of items and could sort them and allow us to process them. So groupBy is a useful useful item. Collection, this collect function, is a little bit similar in the sense that it's kind of like doing a map and a filter at the same time. So you pass in a partial function, something that handles just certain cases, and for those cases, those are the ones that are included in the function as applied. That you get back the results of that function. Okay. There's two others though I want to mention. One is this one, filter with. Okay. So we've seen filter. Turns out there's also a thing called filter with. Okay. Filter with, and okay, it's not defined for all of these. It's defined for certain of them. But filter with basically is like filter when it is supported. It's like filter, but in fact does not create an entirely new collection. All it does is create references to the old collection, to the items in the old collection that map or that retain the appropriate values. So it's not creating an entirely new function out of it. So filter and filter with go together, and this will come into a special use when we're dealing with streams. Flat map is going to be another case that's going to have deep implications in a few lectures, and I'd like to show you that. So I have a lot of examples here for using these. I'd like to go though to flat map. Okay, so with flat map, we are performing a map, but the items that we get out from the function we've given are not themselves just individual elements. They're themselves containers. Okay, and we want to use those. So let's consider our list of values here. Okay, there we go. Suppose we wanted to take this list and we want to in fact extract the values of each of these strings in terms of the characters within them. Okay, so let's say we have foobar, and if I have this, I can go and there's a thing I could say 2-vector. There we are. What has 2-vector done to this? What hath it wrought?
It split it into characters.
All right, split it into characters. So it's a vector of characters here. Okay. Great. So suppose I were to take this thing and I were to say flat map. Well, suppose I were to just say map. Map these to vector. This is what I get out. Now, what seems a little bit weird about that? Suppose I want to get a vector of the characters across these. Suppose I want to count the number of occurrences of each character, right? How many C's? How many O's? How many N's? You might say, oh, okay, we'll vectorize. We'll convert each string to a vector, and then we'll count them up. But what's the problem here? Why isn't that quite working?
Because you still have a collection that's, 6, 7 things long. You don't have a collection that's like now 50.
Yeah, we have a instead of having one collection of all the characters, we have a collection of collections. A vector of vectors. Right? You got it? So it's not quite what we want. We're getting close. We've got the individual elements. We've got the goodies, but we need a big bag of the goodies. Instead, we've got all these little bags of goodies. We want to get all the goodies together so we can count them. Okay? So enter flat map. Flat map. What? Now we have mapped to a vector, but we flattened it so we get only one big vector. Now, part of me likes this example to introduce flat map, because it's a common practical need, actually, to do this. But it turns out that it doesn't do proper service to the fact that flat map is going to have deep implications for us in a few weeks. Flat map is far more than a sort of hacky map that allows you to flatten these things. It's far more than just kind of a convenient hack to allow you to collapse a hierarchy. Flat map is going to be more powerful than map. And we're going to use it in a monadic context to do amazing things. It's going to provide the basis for sequencing computations. And we're going to see how with monads, we can basically modularly string together computations in an extensible form that allows us to perform the same computation but accumulate different types of stuff by wrapping in a monad. And flat map will be the key for doing that. So flat map is absolutely emphatically not a sort of tricky map that kind of happens to have this circumstance. It's actually there's a deeper understanding behind it. Among other things, it will allow us to handle cases where we want to signal exceptional circumstances, where one of these causes an error. And we don't want to throw an exception and just bomb out in the middle of the computation, but we want to have a way of sort of handling that error that's principled and doesn't break our pipelines. So we can describe our pipelines in a beautiful way, in a clean way, a way that's transparent, but it's still robust. It can handle exceptions. It can handle errors along the way. And the way we'll do that is with flat map. We'll have a monad that will be a tri-monad. I think in 340 you had a maybe monad, is that right?
We didn't really touch on any of the more interesting parts of Haskell, to be honest.
There was one class who had a prop, was bringing a problems out on like Scala or something, so we had to replace the props. We went to this a few later.
Okay, so fear not, you will glimpse the beauty in this class. So monads, we're going to have a tri-monad and an option monad, and these are going to allow us to basically say this either holds some value or holds no value at all, and we're going to get out an option from it. And flat map will be the key to that, because each of these gets mapped to an option holding a certain value, and then it gets summarized by an option. But we'll come back to that. Flat map, this is the first use of flat map. Having done that, having done flat map here, what can we do now to, suppose now I want to count the number of instances of each character. I want to count the number of times each character has occurred in there. I want to get back a map, a capital M, which says for each character how many times it occurs in there. What do I do?
You can group by, I guess, identity.
Good. Group by identity.
And then you can flat map, well, if you map values on that, you can take the length of the result vector.
Good.
And then you should have a map of characters.
Good. Okay, so this dot size, something like that. Now this may look a bit mysterious. What's this group by underscore? The point is we're getting in a character, and what do we want to group it by? What do we want to kind of cluster them by? What do we want to?
Equality.
We want to cluster it by that character. So right now we have a vector of characters, and if it's a B, we want it to go into the B bin. If it's an E, we want it to go into the E bin. So the very item is the thing that we want to group by. So we want to group all E's. We want to group all A's. These two A's are going to be grouped together. And let's break down. So I like this idea. Oops, map value. I like this idea, but let's break it down for those who want to follow along. So this gives us this vector, and this is a good way to do it. Grouping by here, we wrote it more succinctly like this. What is that going to give us? Oops. Okay. Oh, okay. It's going to be. It's saying I need the type here. Okay, fine. We'll do it by this. Okay. So here we have each of them mapped to a vector of what?
Copies.
Yeah, these are the different occurrences of it. GG, RR, OOOO. Okay? Okay. And now we're going to perform the map values to take the size of what? What is this taking the size?
It's a collection of copies.
Yeah, so I mean, if I want to write it out more closely, these will be, like occurrences. Probably misspelling that. Occurrences. And Scala is a great language, but it doesn't have a spell checker. Anyway, so here O is mapped to 4 because we have 4 O's. Right? And R is mapped to 2 because we have 2 R's. Reading and writing. The arithmetic is left to mapped to 2. Okay, so ladies and gentlemen, each of these, we have a record of how many times that character has occurred. There. Are you comfortable with that? So pipelined computations, ladies and gentlemen. Taking containers, applying operators successively applying a flat map to a vector, grouping by, mapping the values, getting out a result. Composed operations, one at a time, and that one at a time structure, that sequential one at a time structure, helps ensure modularity. We have each separation of concerns, or each stage is well defined. Each successive stage builds on the results of the previous stage. We're going to have some major benefits extending from this, so we'll be going into more. One of them is the ability to do things in parallel. Apply maps in parallel, apply filters in parallel, and apply even reduces substantially in parallel. Second of all, for Chris's comment, we're going to be able to apply them incrementally. And what that's, particularly in the context of streams, and what that's going to allow us to do is to take a whole pipeline like this, and instead of creating a whole new data structure at every stage and turn, a whole new copy of the data structure, we're going to be able to process each item sequentially along the way as far as it can go. Okay? Successive transformations of that item, and never have to create the intermediate data structure. So that's where we're going to be going with this. But these are the core elements, and I expect them on the final exam to be figured prominently. Map, filter, reduce. Okay? We've seen a little bit about Scala Collections, so we're going to continue to roll out the language. Thank you very much. I'll post the videos, and I'll be posting, probably within the next day, the next take-home exercise. They'll build on that. Thank you.